words will change.
Greetings Bio 6611. In this lecture we're going to continue our evaluation of the use of conditional probability for diagnostic testing, but this time to answer the question from a different perspective, to estimate the probability one has a disease. We'll again look at some brief background and refresh ourselves on the example before examining the idea of predictive values as well as other ways of summarizing the performance. The probability of disease. So this will motivate this lecture set. Suppose a patient arrives to have a diagnostic test administered. Our prior probability that a patient has the disease is what we called previously the prevalence of the disease, or probability of D. The result of the test should alter this, though, to the probability of having the disease given you tested positive. Or potentially the probability you have a disease may be how that would change if you've actually tested negative. Now remember, the effectiveness of the test itself is described by the sensitivity and specificity, and these do not depend on the prevalence of the disease and are usually estimated from studies with a large number of persons who do and don't have the disease. In the case of estimating the probability in the reverse role of having the disease given the test result, we're going to leverage Bayes' theorem to show how we can relate these predictive values to the actual population prevalence. So a brief refresher from what we covered previously. We're going to use Bayes' theorem to ultimately get to this calculation of a posterior probability of an event having the disease based on some prior probability by utilizing conditional probabilities. So again, in our context, we're taking prior probabilities, or the assumed prevalence of the disease in a population. We're going to then incorporate new information, for example, the diagnostic test results, and ultimately obtain revised or posterior probabilities in the form of predictive values. In our context of diagnostic testing, we have two random variables, d sub I, where we have I mutually exclusive and exhaustive disease states, which oftentimes we're going to treat as you have the disease or you don't, so there's two disease states, and then t, representing a positive test result or the presence potentially of some symptom. We see at the bottom here then that we have just a restatement of Bayes' theorem that we'll see actively applied to our calculations. Now remember, we have 50 participants enrolled in our study who have CHD or coronary heart disease and 50 who don't. So we fixed the number based on the gold standard with the angiogram in our study. So therefore our study prevalence, the sample prevalence, does not match the population prevalence, which is actually estimated to be 20% in our population of interest. Again, if you don't have your notes from the last lecture nearby or have this printed out, I recommend you take a second to quickly jot down this table, since we'll be using it in all of our calculations for the remainder of the slides. So let's start by looking at the idea of predictive values. The predictive values of a test depend on the sensitivity, specificity, and the underlying true prevalence or prior probability of having the disease in the population. So again here, prevalence isn't like the sample prevalence we used for sensitivity and specificity, but actually the true underlying population prevalence. Through Bayes' rule, we can then relate the idea of sensitivity, specificity, and that underlying prevalence to this concept we call positive and negative predictive values, or PPV and NPV. One thing to note here, which is a departure from our previous summaries, is that PPV and NPV are very, very dependent on prevalence. Again, using study prevalence is not appropriate when calculating the values for PPV and NPV unless it's from a large prospective study where we believe we can estimate prevalence from the sample. So let's start by defining positive predictive value on this slide before walking through an example on the next. The PPV is the probability you have a disease given a positive test result. So again, we see here in our top line of our function or equation, we write PPV equals the probability you have the disease given a positive test result. Leveraging those ideas of definitions of conditional probabilities, though, we can then rewrite in the second line that's the probability of having the disease and having a positive test result, now divided by the probability of having a positive test result. Based on Bayes' theorem, then we can further work to redefine our calculations and our formula over the next two equations. So the things we do here are just applying the ideas of conditional probability and some of the other properties we discussed previously. Now, one thing I've done here below is I've tried to color code the different terms between our second to last line of the equation, which is written in terms of probability, before we go to that final line where we see that the PPV is defined in terms of sensitivity, the prior probability or prevalence, and the specificity. Take a second to jot this formula down, and we'll be working through an example on the following slide. So let's walk through an example of calculating the positive predictive value. And recall from our last lecture slides, we calculate the sensitivity of our treadmill test to be 80%, the specificity to be 90%, and we're assuming the population prevalence is 20%. We have our formula in terms of probability on the slide here, but I encourage you to pause the video briefly as you work through the calculation yourself before we walk through it together. Okay, let's walk through the calculation for our positive predictive value. We see here we can rewrite these probability statements with the facts we've been given. For example, we know that our numerator is really the sensitivity times the prevalence, or the prior probability. So based on the information we have here, we know it's going to be 0.8 times 0.2. We can then note in the denominator that first term there actually is the exact same calculation, the sensitivity times the prevalence, and then we're going to add to that the probability we would have a positive test given you don't have the disease, or in other words, 1 minus the specificity. So you can note there we have 1 minus 0.9 times the probability someone doesn't have the disease. Or in other words, 1 minus the prevalence, we can just write down here quickly 0.8. Now, if we were to plug all this information into R, or a calculator, let's say, we should get down to an answer of 0.67. Or in other words, the interpretation of the positive predictive value is that if the treadmill test is positive, there is a 67% chance that an individual in the population with 20% prevalence of coronary heart disease actually has CHD. So in this case, it would appear that actually testing positive with the treadmill test doesn't really lead to a huge positive or extremely confident probability. We can also summarize the idea of not having a disease given you have a negative test result, or the negative predictive value, NPV. Much like before, we just see on the slide here the cascading steps we have to start with our, again in probability terms, the probability you don't have the disease in question given a negative test, and working through the different rules of conditional probability, working to apply the idea of Bayes' theorem, and then summarizing our result with the equation below with a little bit of color to help connect the different pieces of the equation to each other in words. Take a second to review this equation, and we'll work through an example on the following slide. Okay, let's continue our example now with the calculation for the NPV. Again, I encourage you to pause your video briefly to work through the calculation yourself before we try it together in a second. Okay, let's calculate the negative predictive value in our case for the treadmill test and coronary heart disease. So we see here in our numerator what we really have is the specificity times 1 minus the prevalence, or 1 minus that prior probability. So we know from our previous results we have 0.9 for our specificity, and that's going to be times 0.8, or in other words, 1 minus 0.2 for our probability of not having a disease connected to our above the probability of having CHD. Looking at the denominator, we then see we have 1 minus the sensitivity here, the probability of not having a positive test given you have the disease, times that prevalence. And so we'll see here we can take 1 minus the sensitivity times the actual prevalence of 0.2 or 20%, And we're then going to add that to the specificity times 1 minus the prior probability, or exactly what we have in the numerator. Again, if we take these values and plug them into R or our calculator, and we churn it out, we should get an estimate of the negative predictive value of 0.947. Or in other words, interpreting it in our context, if the treadmill test is negative, there is a approximately 95% chance that an individual in the population with 20% prevalence of CHD actually does not have the condition coronary heart disease. In other words, because the prevalence is 20% of having the disease, corresponding to 80% of people not having the disease, having a negative finding further reinforces our belief that you probably don't have coronary heart disease. So these represent some of the basic summaries, but there's additional summaries that may be useful in different contexts or to help compare different tests. One such measure is what we call a likelihood ratio. So we may wish to answer just the general question, is the treadmill test even a good test? I have the sensitivity and specificity, I have the positive and negative predictive values. There's a lot to consider in the context, but maybe I can use some other information to help provide another way of looking at it. And this is where those likelihood ratios come in, which are also known as Bayes factors. They are defined in both a, much like many of our cases, a positive and a negative case, where the positive likelihood ratio we see here at the top formula is equal to the sensitivity over 1 minus the specificity, or in other words, the true positive rate divided by the false positive rate. So again, looking at the positive outcome of a test. Then the likelihood ratio negative below here, that's going to look at the negative test, or 1 minus the sensitivity over the specificity, or in other words, the false negative rate, FNR, divided by the true negative rate, the TNR. Thinking about it in terms of our context of diagnostic testing, likelihood ratio positive is the number of true positive results per false positive result. We desire here large ratios, and it serves in this case as a prevalence-free measure of the strength of a positive test. Because again, note here in our equations, we have nothing that has to do with the prevalence in the population. We're summarizing this with respect to the test characteristics of sensitivity and specificity. Likewise, the negative likelihood ratio test is the number of false negative results per true negative. Small ratios here are desirable, and it serves again as a prevalence-free measure. Let's walk through an example first of the positive likelihood ratio test. We've summarized our test performance above for reference, and I encourage you to pause the video to work through the problem yourself before we review our answer together. Okay, so let's apply the equation for the positive likelihood ratio test. We see we just plug in our sensitivity of 80%, or 0.8, minus our, or divided by, 1 minus our specificity, 1 minus 0.9. So we really have here is 0.8 divided by 0.1, or 8. In other words, if we look at our interpretation, there are 8 true positives per 1 false positive treadmill test result that we would expect. So it seems like in general, when we get a positive result, we're going to expect that to be accurate with respect to the likelihood ratio positive summary. Likewise, we can calculate the negative likelihood ratio. Take a second to pause the video and we'll walk through it together. Okay, so for our negative likelihood ratio, we have a very similar equation as we saw before, but now it's 1 minus the specificity 1 minus the sensitivity divided by the specificity. So we see here we have 1 minus the sensitivity of 0.8 divided by our specificity of 0.9. So we really have 0.2 divided by 0.9, or 2/9. Now this is where it can be a little weird to interpret the negative likelihood ratio, so I provide 2 versions here. The first keeps it in terms of what we saw previously in the same setup as the positive likelihood ratio, where there are 2/9 of a false negative per 1 true negative treadmill test result. In other words, we have less than 1 false negative for each true negative result we have. But I find thinking in terms of these fractional components somewhat confounding. So I like this alternative interpretation a little bit more, although both are perfectly right. In the alternative interpretation, we will instead work to put them on a more whole number scale, where we say there are 2 false negatives per 9 true negative treadmill test results. So in other words, we can see here that we do have a slightly higher or worse maybe negative likelihood ratio relative to the positive likelihood ratio. But when you put it in terms of whole numbers, we can see that for every 9 true negatives, we can then expect there to potentially be 2 false negatives. There are other summaries though, and we're going to work our way to getting to the idea of a posterior probability summary, but to get there we first have to discuss the idea in more detail of odds, starting with the posterior odds that we want to calculate after we first calculate the prior odds. So we can leverage the likelihood ratio calculations we did previously and then incorporate the idea of prevalence through the odds. For some terminology and notation, let's let O of D represent the prior odds of having the disease, and from our prior probability or the stated prevalence of having the disease, we can calculate the prior odds. And it's this just simple relationship here, which is actually generally true for any calculation going between probability and odds. The odds will be equal to whatever the probability is divided by 1 minus the probability. Likewise, though, if we had, let's say, the odds, but we wanted the probability, we can also work backwards that way, or plug in the odds divided by 1 plus the odds to get the probability of interest. And just for completeness, we can note here that above it was the odds of having the disease. We also can calculate similarly the odds of not having the disease, which here we see is the exact same setup of the probability of not having the disease divided by 1 minus the probability of not having the disease, which we can also though rewrite in our next step here as just 1 minus the probability of having the disease or prevalence divided by our probability of having the disease, the prevalence. Based on the calculation of the prior odds in the previous slide, we can see the direct connection when we reevaluate the idea of how we get to a posterior in the context of Bayesian analysis. What we see here is really just the posterior equal to some prior belief times some revised information based on a likelihood. So in our context of actually trying to calculate the posterior odds and the eventual posterior probability of having or not having the disease, we can see that we have the posterior odds of having a disease are equal to the prior odds of the disease times the positive likelihood ratio. Or alternatively, the posterior odds of not having the disease are equal to the prior odds of not having the disease times the inverse of the negative likelihood ratio test, or we see at our right hand side 1 over the negative likelihood ratio. So our interpretation of the posterior odds, and here I have in square brackets the interpretation if we were looking at not having the disease, but the interpretation of the posterior odds of having the disease D are that after observing the test results for an individual, we are x to 1 in favor of them having the disease. Or, in other words, in favor of having the disease, where x is our posterior odds that we calculated above. Now this leads us to the idea of posterior probability, because honestly, I find odds to be a somewhat challenging thing to interpret and explain, and honestly I have to think about it every time I try to decipher what they're trying to say. That's because odds range from 0 to infinity, and they represent that ratio of outcomes. Many people prefer probabilities because they range nicely from 0 to 1, and most often they have a more intuitive understanding, or at least we encounter them more in our daily life. Now, fortunately, based on some of the previous relationships we discussed before about the relationship of the calculation between the odds and the probability or vice versa, we can easily take our calculation of the posterior odds and calculate the posterior probability of an outcome, which again will be a nice interpretation because it'll say how much we believe someone is to have a disease or not have the disease based on the result of the test that we observe. So let's see some examples of these calculations, and we'll start with calculating the posterior odds and probability of having the disease. Again, at the top, I've now given us the information to remind ourselves what we need here, but the positive likelihood ratio is equal to 8, and our prevalence is 0.2. take a second to pause the video here and work through these calculations on your own, and then we'll work through them together and put them in the context of our interpretation at the bottom of the slide. Okay, let's first start with that step of calculating the prior odds of having the disease. Here we see it's a pretty simple calculation again of just taking that population prevalence divided by 1 minus the prevalence, or 0.2 divided by 0.8, which will equal 1/4. We can then go to the next step of calculating our posterior odds of D. So we then plug in our prior odds of D we just calculated, 1/4, times 8 for our likelihood ratio positive value we calculated before, which is equal to 2. Then again, we just have this nice simple relationship to translate the odds back to the posterior probability, where we put 2 over 1 plus 2, or 2/3. In other words, putting it in the context of our interpretation, after observing a positive treadmill test, or TT, our odds in favor of a person having coronary heart disease are going to be 2 to 1. Or the posterior probability of having the disease is going to be 67%, which is representing the change we saw from our original prevalence or belief that someone had the disease of just being 20% before we saw the result of the treadmill test. Likewise, we have an example here for calculating the posterior odds and corresponding probability of not having the disease. So I'll give you a second here to pause the video before we work through it together. Okay, let's start by calculating those prior odds of not having the disease. Again, from our equations we saw before, it's simply going to be that 0.8, or the probability of not having the disease, divided by our prevalence of 0.2, which will be equal to 4. Then using our formula we have here, we just take that prior odds of 4 times 1 over our negative likelihood ratio test of 2/9. And we can see we can do a little work to make that a little more friendly to work with. Where you can see we have 4 times 9/2, or in other words, 18. With this value, the posterior odds of not having the disease, given someone had that negative treadmill test result, we can then plug that into our posterior probability, where we take 18 over 1 plus 18, or 18 divided by 19, which will be approximately equal to 0.947. In other words, in the interpretation of our problem, after observing a negative treadmill test result, our odds in favor of not having coronary heart disease are going to be 18 to 1. Or again, in a more, I think, interpretable way, the posterior probability of not having the disease is going to be approximately 95%, which represents the change from our prior probability of 80% of not having coronary heart disease. So again, we were already fairly confident that any random person would not have, at least not be in favor of likely of having coronary heart disease, but the treadmill test negative result further reinforces this idea and makes us more confident in that conclusion. So I do want to highlight now a little Easter egg connecting the positive predictive and negative predictive values with those posterior probabilities. If we look back at all of our calculations, we can see that actually the positive predictive value and the negative predictive value are the same as our posterior probabilities of having or not having the disease. So it turns out if we're interested in the posterior probabilities, we can actually just look to calculating the predictive values instead of going through all the rigmarole of calculating the prior odds, the posterior odds, and the likelihood ratio tests to get to those posterior probabilities, which is a nice shortcut. That being said, sometimes it will be helpful to calculate the odds or the likelihood ratios for other summaries. And so we're going to end here with just this one sheet to summarize all we've talked about. We have our confusion matrix that we're just summarizing briefly again here on the top right of our slide. Everything we see on the left-hand side column are prevalence-free measures of the test performance. So again, none of these have anything to do with the actual prevalence in the population. Our calculations then for the positive and negative predictive value do depend on the population prevalence, and therefore we should use the more complex equations earlier in these slides. However, if we did a study design that we believe the study prevalence is a good estimate for the population prevalence, in that case we can actually take advantage of the shortcut and also have these calculations where we can take the cells of information we've observed and calculate the positive and negative predictive values respectively. So this will wrap up our evaluation of a disease status gold standard to a test that has a positive or negative outcome. And in the next lecture set, we'll look at what to do if we have a test with multiple outcomes or a continuous range of values.